All right, let's pick up with where we left off last time. So, last time, we wanted to solve the rate problem. And we saw that the slope was connected to rate of change, in the sense that it somehow told us about speed or velocity, if you want to get technical. This basically is how fast one quantity changes in relation to the other. And we had that example of that thing that we were measuring distance in miles and time in hours, and looked like this. And then we could say that the speed was 50 miles per hour, right? That was the slope. Now that is a measure of how fast things are moving. In what sense? In the following sense. So it says, basically what this is saying, every time you move 1 unit on the horizontal axis, you would have moved 50 units on the vertical axis. Instead, this is saying that distance changes 50 times faster than the time units. That's how you can actually express this interpretation, right? Okay, so if I have one function tracking distance and another function tracking time, who's faster? The distance function is going to be faster. By how much? 50 times faster, right? Me saying 50 miles per hour, that's what that means. The distance is changing 50 times faster than the time is changing, right? And it turns out that that number was actually exactly the slope. The slope measured that number. So the slope was connected to rate of change. It actually could tell us how two quantities, how fast are they in relation to each other. We wanted to generalize this. To say things that aren't straight line, to curves, right? So if I have some random function, can I do the same kind of examination? Is there some way to find a slope so that I can talk about this is moving faster than that, or this is moving faster than that? How can I compare rates of change? And so given some f of x, right, and this was some curve thing, so let's just make it one easy curve like that, just for simplicity. We wanted to be able to do this thing, but of course it's not a straight line, so there is no one slope. You have to do it point by point. So you had a point of interest that you wanted to do this for. How would you find the slope of that curve at that point? It was the goal. And the idea was, surprisingly, kind of think like a flat earther, basically. So yes, it looks curved, but there's a certain scale where something that is curved looks flat, right? We all hopefully know that the earth is round, but to some people it looks flat. Hey, it's flat. This is because we're on such a scale that the curved part starts to look flat. So what we basically do is we kind of zoom in, right? So if you zoom in far enough, right, this thing that's all curvy right here, it'll start to look flat. It'll start to flatten out mostly. So sure, there'll always be some slight curve, but the curve is less noticeable the more you zoom in. And so the idea was, can we create a line now? Because the more we zoom in, this will start to look like a line. Is it possible to create a line that's actually going to do that? So at this point of interest, I want to create a line. A straight line, because that's how I know, that's the thing I know how to measure the slope of, in such a way that if I zoom out, the line and the function are doing pretty much the same thing at that point. They become less distinguishable the more I zoom in, right? So the idea is we want to approximate the curve with a line. And this line was what we call the tangent line. So a tangent line, what it really is, if you wanted a definition, it is a line that touches a curve at one point such that if we zoom in, the line, the tangent line and the curve start doing the same thing. Right? They become indistinguishable the more you zoom in. When this thing starts flattening out and I zoom in, it will start to look more and more like that straight line. Right? And then, last time we saw how to measure the slope of this line. Now, if we know about a line, we need two things usually, two pieces of data to find a line. One is we can either have the slope and a point. If you give me the slope and a point, I can tell you what the line is. In this case, we don't know the slope because the slope is in fact what we're finding. The only other way to find a line is to have 2 points. And so that's what we did last time. If we wanted to find this line, how do we actually get to it? Well, we start out with 2 points, right? So one of those points is my point of interest. And just pick some other random point. And the goal is take this point and move it close to that one. How do we get that done? With a limit. The limit allows us to approach. Right? That's what a limit is about. It's not about being at the point. It's about examining what happens as we get close to the point. And it turns out that the secant line connecting those 2 points will transform itself into the tangent line that you want if you just take that limit. So last time we found the slope of this line, slope of the tangent line, is going to be given by a certain limit. It was given by the limit of the difference quotient. As the denominator approaches 0. Now that's important, muy importante. To the point that it actually warrants a whole definition unto itself. Now, I'll talk about notation for a little bit. In terms of notation, because I don't want to have to write the slope of the tangent line every single time. There are two main notations that we're going to use to express this, this formula. There's Newton's prime notation. All right, so Isaac Newton, one of the people who are credited with developing calculus the way that it's used today. The other person is the German mathematician Leibniz. So you have Newton's prime notation and the Leibniz notation. So for the function f of x, what is the thing, what is this limit actually called? Newton called it f prime of x. So he used this, that notation there to talk about that limit. Right, so that's called a prime notation. Right? So this, whenever you see that, it actually means the limit as h approaches 0 of f of x plus h minus f of x over h. That's what it means. This thing here is called a prime. And this is pronounced. So f prime of x is pronounced f prime of x. Because not everyone will tell you this, but sounding like you know what you're talking about is just as important as knowing what you're talking about, right? So you don't want to go around, oh, f apostrophe, like no, what's f apostrophe? No, it's called a prime. F prime of x is how you will now say that. It's called Newton's prime notation. It looks like an apostrophe, it's not really an apostrophe. It's a very ostentatious apostrophe. It's actually like a little notch like that. That's all it's really doing. course, when you're writing it by hand, you just write that. But it's not an apostrophe, technically. So that's one notation. You can write f prime of x. And what does that mean? Well, it's this limit. What is that limit? That's the guy that allows us to find the slope of a tangent line at some point of interest. Leibniz used a different notation. He used this. Right? So where y is equal to f of x, he liked to replace the function with just another variable, some independent variable, and he called it dy dx, and that's it. So this is also equal to the limit as h approaches 0 of f of x plus h minus f of x over h, where your f of x is just replaced with y. But this one, dy dx, pronounced dy dx. That's how we say it. Dy dx. So whenever I say dy dx, everyone knows I mean dy divided by dx, and everyone would know what I mean. Oh, it's the slope of the tangent line at this point. Right? And that one kind of came from the fact that, you know, how slope of a line. I don't know why Newton decided that on that notation, actually. But slope of line we know is delta y over delta x, right? Where that's the Greek letter delta, and we usually use it to represent change in y over change in x. So that's the analogous to the English letter d. Leibniz decided, instead of the delta, let's use d's and give that a different connotation. So when I'm talking about the slope of a tangent line specifically, I'm going to use a d instead of a delta. That's how he decided to write it down, right? So that's the Leibniz notation, dy dx, right? Newton just decided to put a notch on his function's name, and just like, that means the derivative, or the slope. And this leads to a definition. So let f of x be a function. The slope of the tangent line to f of x at any x value is given by, I'm going to use Newton's notation. A lot of times I'll actually just use Newton's notation because it's easier to write down. Not because it's necessarily more correct, but it's just easier to write down a lot of times. It's given by this expression. Now this is an important equation. You need to have this memorized. That's going to be important. And of course, provided it exists, it's a limit after all. It's possible for it to not exist. But if it can exist, it means we can find the slope of the tangent line, and it will be given by that particular limit. And we call this limit the derivative of f of x with respect to x. Sometimes you might correct with respect to x. Now, just the fact that it's called a derivative should tell you that it's important, because normally math people are horrible at naming things, or just like not very creative. They tend to name it whatever it's talking about. So it's like, oh, we have this theorem that tells us that if you consider this function, it attains all intermediate y values. What do we call it? Intermediate value theorem. Or, hey, we have this formula that tells us how to find the mean rate of change. What do you want to call it? Mean value theorem? Here it's like, hey, I found a formula that gives us the slope of tangent line. Derivative. Like, where did that word even come from? I don't know. I don't know why they call it the derivative. It's called the derivative, but it's definitely an important thing. And it is, in fact, it looks very humble, but it's a big deal. It solves the rate problem, actually, in a very sophisticated way. So that's called the derivative. One thing you're going to want to know, also, is interpretations. Right? When you see f prime of x, or you see dy dx, what do you think? Right? So contrary to popular belief, you don't take a derivative when in doubt. There's a specific reason why you would take a derivative. There's a specific way that you would interpret this quantity. Right? So one, you would think of it as the slope of the tangent line to f of x at x. Right? So if you're in a situation where you want to find the slope of a tangent line, if that's your goal, the derivative is what you should be looking for. Right? Now, this is also more generally the slope of the function itself. We actually defined it to be the slope of the function. Right? So now, in general, it's not the slope of the function, but at a specific point, when we zoom in, the function and the tangent line are doing pretty much the same thing. So the slope of the tangent line might as well be the slope of the function itself. So when we want to talk about the slope of a function in general, we can actually use the slope of a tangent line at a point of interest to find the slope of the function itself. How you can also think of this is, well, it gives you a formula for the slope of the tangent line, and I'll explain that a little bit more. Formula for the slope of the tangent line. Another way to think of it is in terms of rates of change. How fast f of x is changing in relation to x, right? Now, f of x and x, right? Yes, it's a math class. For us, usually f of x is just f of x and x is just x. But in the real world, f of x is going to represent something. It's going to be some quantity. It's going to be a distance, or it's going to be the size of something, or it's going to be the profit that you're making if you have a business. It's going to have some interpretation on it. And so x is going to also represent something else. And so you want to talk about how fast is this thing moving in comparison to this thing. So someone wants to say, this is moving 50 times faster than that thing. How would you come up with such a determination? You take a derivative. Right? It talks about rate of change. How fast something is moving is going to be given by the derivative. Slope of a tangent line, the formula that gives the slope of a tangent line is talking about the derivative. You would find a derivative in these contexts. And consequently, there are going to be a few other contexts where you're going to know you want to find a derivative. But these are the main ones. If you want to figure out speed, derivative. If you want to figure out the slope of a tangent line, derivative. Later on, we're going to talk about maximums and minimums. If you want to find maximum and minimums, turns out derivative is going to be useful. Increasing and decreasing, derivatives are going to be useful. But we'll get to that. But the basic foundational interpretation are these. Right? So derivative is useful in these situations. Let's actually do an example. Now this example is actually, I'm going to make it look pretty much like a problem I would actually ask you. So like on test 1, there's going to be a problem like this, for sure. Like, no doubt. Like I'm going to ask you this, so you can't say I never told you. Okay? It's not going to be, I'm going to change the function, but the question is going to be essentially the same. So let f of x be equal to x squared. Nice function to start with. It's not so simple to just be a silly example, but it's not so complicated that you'll get lost in the complication. So it's a nice instructive example, x squared. Pretty much every textbook is going to do this as one of the first examples of using this idea. Use the definition of the derivative. of the tangent line to f of x at, say, x equals 4. Okay, that part B. Find the equation of this tangent line. Wording might be slightly different, but that's essentially a question I will ask you. I'm going to give you a formula. I'm going to ask you to use the definition to find the slope of the tangent line, and then I'm going to ask you to find the equation of the tangent line. Okay? So here we have y equals x squared. So now you're going to go in and you're going to do that definition. So we know that f prime is the slope of the tangent line. This is literally one of the interpretations of the derivative. You need to find the slope of a tangent line, you find f prime. This is going to be the limit as h approaches 0 of f of x plus h minus f of x all over h. Formula is very important. I'm in fact going to ask you to regurgitate that formula from time to time, definitely on the next quiz I'm going to ask about it, so you need to remember. How do you remember something? Write it down every time you use it. Eventually you'll remember. So write that out. Now let's actually plug in. So if my f of x is x squared, what is f of x plus h?
X plus h squared.
X plus h all squared minus f of x, which is just x squared all over h. Now I need to compute that limit. How do I find that limit? Yeah?
You could expand.
Okay, expand? Right, because you can't plug in. So what else can we do? Expand might be a good idea. What does that expand to?
X squared plus 2xh plus h squared minus x.
X's kill each other. And now we have the limit as h approaches 0 of 2xh plus h squared all over h. And we can cancel this h right here, right?
No.
Can't cancel the h's, right? That's canceling cross sums. Just want to see if someone's going to say yes, I can throw the marker. Okay. What do we do then?
Factor.
Okay, factor out the h. Now we can cancel, because canceling cross multiplication. Now what's the limit? 2x. Now I'm in a situation where I can plug in 0 for h, and it'll make sense. 2x is going to be the answer. Now, what does that mean? Not necessarily a part of the answer, but I just want you to appreciate what this means. This means if your f of x is x squared, then your f prime of x is going to be 2x. And what that is, this is a formula for the slope of the tangent line. At x. Right? Which means, if I look at this question now, it asks me, find the slope of the tangent line to f of x at x equals 4. This means I want x equals 4. So, this means the slope of the tangent line at x equals 4 is, well, it's going to be this function, f prime, but I want to now evaluate it at 4. Now, f prime of 4 is going to be what?
8.
Well, it's 2 times 4, which is 8. So 8 is going to be the answer to part A. The slope of the tangent line at x equals 4 is 8. that's part A. Okay, B. Now I want to find the equation of the tangent line. How do I do that? What's the equation of the tangent line? What would the formula for a tangent line look like? Yeah?
Isn't it just the limit of each booking zeros?
This?
Yeah.
No, this gives you the slope of the tangent line. Here I want the equation of the tangent line. How do I find the equation of the tangent line? Yeah?
Can you use the point slope formula?
Point slope formula. So, I mean, one thing you have to remember is that a tangent line, it is a straight line, right? I mean, it's going to look like y equals mx plus b or something like that, right? Essentially, you want to find that formula. Now, how do you find the equation of a line? Well, there are a couple ways. You can find the equation of a line if you have 2 points. You can also find the equation of a line if you have a point and a slope. In this case, we have the slope, so the only other thing we need is a point. So, from above, our m in this formula, which is the slope, is equal to f prime of 4, which is 8. So our slope is 8 in this case. Now, this means the point, so this is the slope. Now I also need the point. How do I find the point that I care about? Yeah.
Would you plug in 4 to the original equation?
So when x equals 4, I want to know what is the y value for that. Well, your y is going to be 4 squared, which is going to be 16. So this means the point is 4, 16. So I now have a slope and I have a point. I can find the equation of a line using that. This means, for the tangent line, say use point slope from y minus y1 equals m x minus x1. That's y minus 16 equals m x minus 4. And that's the equation of the tangent line. If you want it in y equals mx plus b form specifically, you could also do that. Just that's 8x. 8 times 4 would be 32 plus 16. So you get 8x minus 16. So that's in mx plus b form.
Do you prefer like which way we do it on the test, or?
In general, I don't care, but just read the instructions probably. If the instructions say write it in a certain form, make sure you do it in that form. But in general, if I don't say, I don't care. So that would be the equation of the tangent line. Now, I want you guys to see what this means. So let's actually have a visual of the situation here. So basically, we had our function. We had y equals x squared. So this was our curve. Now someone told us, okay, I care about what's happening at 4. So at 4, there's a certain point here. Of course, the y output for that is going to be 16. I want to find the equation of the tangent line at that point. Meaning, I want to first construct a line so that it passes through that point in such a way that if I were to zoom in, the line and the function are doing the same thing. What would the equation of such a line be? Well, we just found it. It's y equals 8x minus 16. That would be the line that gets the job done. Right? And which means that this here is going to pass through minus 16 with positive slope 8. Right? And again, interpretations can vary here based on the situation. So if I were to again say this is y is measuring distance in miles, x is time in hours. Another way I can interpret this is that, hey, you know what? After 4 hours, this object will be traveling at 8 miles per hour. I'd be able to tell you how fast this thing is moving. I'd be able to tell you, at that point, the distance is changing 8 times faster than the speed is changing. Right? I can say whatever's on the y-coordinate, whatever interpretation that has, that thing is moving 8 times faster than whatever the interpretation of this thing is. Right? So lots of interpretations you can have, but geometrically, this is actually what you're seeing. We're given this curve and we're asked, construct a line to this curve that will be approximate that curve at the point x equals 4. Turns out that's the perfect line to do it. Any other line you picked would not have gotten the job done. Any other line that passes through here or here, any other line. When you zoom in, they're not going to look the same. But with this line, this specific line, the more you zoom in, the more they look alike. Right? I can use this line to approximate the curve. Another thing that you probably want to appreciate from this is that the slope of the tangent line had an x in it. It had a variable, which means it could change. Which, again, looking at this picture, you can see that that makes a lot of sense. Because if someone were to tell me a different point, let's say -4, the tangent line over here would have a negative slope. It would be completely different from the red line we just found. How would I know what the slope of that line is? Well, it's 2 times the x value. Slope at this line is going to be -8. Someone asked me, okay, what about -2? What is the slope of that line? -4. Okay, what if we're at 5? What is the slope of that line? 10. Right? This guy literally gives me a formula where I can find the slope of the tangent line at any value of x. If I want to know, okay, at this point, how fast are we moving? Double whatever the x coordinate is. How fast are we moving when x is 10? 20 units per time unit. Right? 2 times x will give you the slope. Right? So that gives you a formula for the slope of the tangent line. So that's actually what we did. This was what we were given. The red line is what we found to get a certain job done. Now let's actually do some more examples. Now we will get to interpretation soon. Right now I just want to make sure that we understand computationally how to approach this. Okay, find slope of the tangent line. For the following. Let's say my function is a constant. What would the slope of the tangent line be? Or give me a formula for the slope of the tangent line. Let's say my function is a constant times x. What would the slope of the tangent line be? Let's say my function is 1 over x. What would the slope of the tangent line be? Let's say my function is the square root of x. What would the slope of the tangent line be? So A, f of x equals c. What do you think the answer is going to be? If you think about it. Like, what does the graph of this look like? Yeah? It would be 0. Why? What would the graph of this look like? It's just a horizontal line, right? Now, if someone asks you, if I'm here, what is the slope? It's 0. Right? What is the slope over here? It's 0. What is the slope over here? It's 0. It's always 0 because it's flat. There's no rise. Right? Rise over run is always going to give me 0. So I expect the answer to be 0. But let's actually do the calculations. Do our calculations agree? We're asked to find f prime of x. What is that? Limit as h approaches 0 of f of x plus h minus f of x over h. Right? Keep writing it down until you remember it. Okay, so if my f of x is c, what is f of x plus h? just c. Right? It's not going to change. Right? Remember, f of x plus h means replace all x's with x plus h. There are no x's to replace, so it's just c. There's no x. Now, of course, c minus c, this should be h. C minus c is, well, that's 0, and that's 0. So yeah, makes sense. 0. Right? Our definition matches up with what our intuition told us the answer should be. Which isn't always going to be the case. Sometimes your intuition can lead you astray, but the calculations tell you you're right. Here's a short way to express this idea. Short way to express this. Now, over time, I'm going to expect you to know about how to find the derivative to certain functions, and I'm going to write these rules down in a certain way. I just want to make sure you understand the notation. One way to express this is to use a Leibniz notation, d dx of a constant. Right? So I'm stating the derivative with respect to x of this function over here is 0. So I can state that as a rule. And that's a rule that you know now. The derivative of any constant is 0. What's the derivative of 5? 0. What's the derivative of 7? 0. What's the derivative of 17.9? 0. What's the derivative of pi? 0. Doesn't matter what the constant is, the derivative of any constant is going to be 0. Because you plug in the constant into the formula, you're always going to get 0. Derivative of a constant is 0. That's like a rule. That's something that we now know. You shouldn't have to derive it every time. Now you just know. Derivative of a constant, 0. Let's go down to B. What if we look like a constant times x? What do you think the answer should be? Yeah.
C.
It's going to be the c, right? That's like mx, right? The c is like the slope here, right? So c should be the answer. What does our definition say? Limit as h approaches 0 of f of x plus h minus f of x over h. Okay, so if my f of x is cx, what is f of x plus h? Yeah? Kayla?
Cx plus ch.
All right, c times x plus h, which is going to be cx plus ch. The cx's are going to kill each other. You're going to have a limit as h approaches 0 of ch over h. The h is cancelled. Now the limit of a constant is just a constant. That was actually a rule that I gave you last class. So c is the answer, which again makes a lot of sense. Very intuitive, in fact, right? This is just a line where the slope is c. In fact, this is actually a line through the origin where the slope is c. So another way I can write that is the derivative of c times x is just going to be c. More specifically, something that you should just know, the derivative of x, of course with respect to x, is 1. And that's just by plugging in c equals 1. If c equals 1, we end up with this, and that you can know as a rule. Derivative of x is 1. So that's something you should know, but you should also know the interpretation behind it. What does it mean to say the derivative of x is 1? You should know that. What about 1 over x? Now this one isn't as obvious, right? So, I mean, sure, you know what the picture looks like. There's nothing about that that's going to tell you what the slope would be. Like if I pick a random point here, drew a tangent line, what's the slope there? Can't really tell from the picture. Right? These are kind of obvious. It's a horizontal line, slope is 0. This is just a line with literally the slope is c, so yeah, the answer is going to be c. Very intuitive. What is the slope of this function? Well, let's figure it out. F prime of x would be equal to the limit as h approaches 0 of x plus h minus f of x over h. Write it down every single time. So now, what is f of x plus h here?
1 over x plus h.
1 over x plus h, 1 over x, all over h. So now we want to find this limit. You'll notice that you have a compound fraction here. Quickest way to get rid of a compound fraction, deal with it, simplify it. Yeah?
You multiply by the common denominator.
Multiply and divide by the LCD, so we multiply and divide by x times x plus h. So in the top, you're going to multiply that, in the bottom, you're going to multiply that. So now in the top, if I take x times x plus h times this, the x plus h is cancelled, and I'm left with x. If I take x times x plus h times that, the x's are going to cancel, and I'm going to left with x plus h in parentheses, very important, parentheses. Over, in the denominator, I'm going to have hx x plus h. Never expand the denominator. Now the x's are going to kill each other, we're going to have minus h left over. Now the h's cancel. I'm going to minus 1 over x times x plus h. And now I can plug in h equals 0, because the denominator is not going to be 0, except if x is 0, but of course x is not 0, because we wouldn't have a function in the first place. So I can plug in h equals 0 here, and we have minus 1 over x squared. So now you can know, so this is just another thing we know now, the derivative of 1 over x is minus 1 over x squared. So that says derivative of 1 over x is minus 1 over x squared. In other words, that is the slope of the tangent line at any value of x. So if this was at 2, what was the slope of that line I just drew? Well, I plug in x equals 2 there, it's minus a quarter. What about at x equals 1, what is the slope? It's minus 1. What if we're at minus 3, what is the slope? Minus 1/9. That's a formula that's going to give you the slope of the tangent line at any point. Let's stop there, do this one for next time. And of course, next time we'll have a quiz on all this stuff, everything we did this week, up until being able to find a derivative using this definition. So, we'll stop there.